All right, now we are going to talk about digital signature algorithm. So before describing how this algorithm works, I will briefly describe what a digital signature is, okay? A digital signature is a number dependent on some secret known only to signer. In other words, the signer's private key, and additionally on the contents of the message being signed. So actually you are digitally signing a message, but as an input you use the message. Actually, in practice, we use the hash of that message. Then we use our private key and obtain a number actually. So that will be our digital signature. Due to the sizes of the signatures, hash of the message is signed instead of message itself. So this is important. People think that they are really signing the message itself, but it is not practical. For instance, think about signing drivers. Nowadays, for instance, graphics drivers are more than 1 gigabyte. Signing it using a digital signature will be even larger, so it will be very impractical. Okay, so we just sign the hash of a message. So signatures must be verifiable. If a dispute arises as to whether an entity signed the document, an unbiased third party should be able to resolve the matter equitably without requiring access to the signer's private key. So that is the whole point. So this is what we are going to use in a blockchain. So disputes may arise when a signer tries to repudiate a signature it did create. So assume that you send somebody some Bitcoin, you signed the transaction, then if you deny that transaction, actually it wouldn't work because everybody will be able to check the correctness of the signature by using your public key. And a contrary thing may arise. A dispute may arise when a forger makes a fraudulent claim. So assume that you have Bitcoins and somebody might try to transfer them as if they own them. So they will try to forge some signatures, but again, if the signature algorithm is secure, this will be easy to detect, okay? So digital signature schemes can be used to provide the following basic cryptographic services: data integrity, the assurance that data has not been altered by unauthorized or unknown means; data origin authentication, the assurance that the source of data is as claimed; non-repudiation, the assurance that an entity cannot deny previous actions or commitments. So these are actually the three services these digital signatures provide. So I actually said this at the beginning, but I say it again: a digital signature algorithm is not an encryption algorithm. Okay. Yeah. So my instincts were right. I actually added here. So a digital signature algorithm is not an encryption. Okay. Digital signature algorithms are not encryption algorithms. I actually mentioned this at the beginning. So throughout this course, we will have many misconceptions that I will explain why they are wrong. So I think this is number 5, and we will see many more misconceptions throughout our lectures. So digital signature schemes are commonly used as primitives in cryptographic protocols that provide other services, including entity authentication. So there are many standards for that. We have FIPS, but it is now obsolete. I think it is no longer valid since 2015. So, but entity authentication is also in a ISO standard. This is a very old standard, but I just checked and it is revised in 2019. But there are also papers using this kind of protocols like Blake, Wilson, and Meneses. It also provides services like authenticated key transport. Again, there is an American standard for that, ISO standard for that, and there are also the same paper from here. It also provides authenticated key agreement, so you can use digital signatures in this kind of protocols. Again, there is an ISO standard, but there are also some other papers where this kind of cryptographic protocols are provided. Okay. So with this basic information about digital signatures, let's see a standard about this. So there's a digital signature algorithm, which is shortened as DSA, but it is also a standard, so it is also known as digital signature standard. So DSA or DSS are the same thing. So the DSA was proposed in August 1991 by the US National Institute of Standards and Technology. We shorten it as NIST. It was specified in a US government Federal Information Processing Standard, FIPS, but I told you that this is no longer valid since 2015. The DSA can be viewed as a variant of the Algama signature scheme. So this is actually why I showed you Algama as an example, because the digital signature algorithm works like the variant of this Algama scheme. So its security is based on the intractability of the discrete logarithm problem in prime order subgroups of ZP star. But I just recently checked the current draft of FIPS 1865, and it states that prior versions of this standard specified the DSA. This standard no longer approves DSA for digital signature generation. DSA may be used to verify signatures generated prior to the implementation date of this standard. See FIPS 186-4 for the specifications of the DSA. So at the current version 186-4, the DSA is there, but this newer version is currently in a draft version, and apparently when it becomes active, DSA will no longer be a standard. But in this document, in this one actually, you can see that there is elliptic curve digital signature algorithm there, which is valid. And in this current version, the draft current version, we also have elliptic curve digital signatures, but you will see that there is also adverse curves and so on. So this apparently this new FIPS will be valid in the following months, I guess. So let's look at how the digital signature algorithm works. So it contains a few steps. First is the parameter generation. So before starting generating keys, we have to first agree on the parameters. So first we have to choose a good hash function, because we are going to sign the hashes of messages. So in the early versions of this standard, you will see that they were using SHA-1, which provides 80-bit security. But SHA-1 is no longer secure for us, so this is why I gave examples as SHA-2 and SHA-3, and Bitcoin uses SHA-2. Okay, so first you choose your hash function. Of course, Bitcoin does not only use SHA-2, but it uses 256-bit version of SHA-2. In other words, SHA-256. So it actually determines your security, bit level security. This is why if you use SHA-2, you have to choose your key length L as 3072. So if you choose SHA-2, then you have to choose N as 256 bits and L as the 3072 bits, which will be your key lengths. Now that you fix these numbers, you choose n bit prime q, you choose L bit prime modulus p. So this is why our modulus size is this, okay? But you have to choose p such that p minus 1 will be a multiple of q, okay? Choose g, its multiplicative group order modulo p must be q. So these are your parameters, p, q, and g. So you can share this with n. If you want to communicate to n people, you can actually share this public information to n of them. But if you prefer, you can generate these parameters differently for every other communication with every other entity. But in Bitcoin or different cryptocurrencies, we are going to see that we will choose elliptic curve at this point, and that elliptic curve will be used for every communication for everybody. So we are not going to use different parameters for different people. We will share it with among everybody in the system. Okay, so this is your parameter generation. You actually determine your security, your algorithms, and then you choose these numbers. Now we move on to key generation. As a user, like in the Algama algorithm, you randomly choose a secret key X, where X is between this number 0 and Q. Okay, then you calculate G to the X modulo P, which will give you Y. So this will be your public key. So the main idea will be that you will use X, your secret key, to sign a document or a message, and everybody will be able to verify the correctness of that signature by only using your public key. So that is the main idea. This is why we are having public and private keys. So this part is like the Algama algorithm. Now that we have chosen, we have our parameters, we have our keys. Now it is time to sign a message. So assume that you are going to sign a message. For every different message, you have to randomly choose K, a random number for that message. And this has to be kept secret, okay? If you use the same K twice for signing a different message, then actually your secret key is lost. People can recover your secret keys. And when we talk about Bitcoin security, I will give an example where this actually happens. Due to a bug, people use the same random number K twice for 2 different transactions, and their Bitcoins were stolen afterwards. But of course, they're not using digital signature algorithms, I mean the Bitcoin, but we are going to use the elliptic curve version of that. But now we first see how the standard version works. So in order to sign a message, at the first step, we chose a random number K. Then we calculate R, which is G to the K modulo P modulo Q. Then M is the message that we want to sign. So we take the hash of it. Then it's X plus R, sorry, X times R. We also multiply it with K inverse. This is the multiplicative inverse. And the modulo Q of this result is equals to S, okay? So at this point, R and S is your signature, okay? So X is your secret key, so this is why you can use it here. And K is the random number you chose, so you calculate the multiplicative inverse of it, again using the extended Euclidean algorithm. So you can easily calculate R and S. So, and other people cannot do it since K is secret here. They cannot capture K from R because it equals to the discrete logarithm problem. And so you can see how we sign it. Now let's see the verification. If we sign something like this, people looking R and S and also the message M will be confident that this is signed by you. Okay, so you give the signature to them and also the message that you signed. So they do the following. They calculate the S inverse modulo Q, which they say it is now W. They also take the hash of your message, calculate it with this number, modulo Q, and say this is equals to U1. Then they calculate U2, which is R, which is taken from your signature, and they multiply with W modulo Q, and they say that this is U2. Then they calculate G to the power U1 times Y to the power U2 modulo P modulo Q, which equals to V. So if this number V equals to R, then this means that this is a valid signature, okay? Actually, you can open this up and see that R calculated here actually equals to V from this computation, okay? I'm not going to go into much detail because I will show you why this verification works in elliptic curve digital signature algorithms, okay? So if we go back, we start with parameter generation and we share this knowledge, these are public. Then we choose our secret key and obtain our public key. Our public key is also public. So we sign a message doing these operations and everybody can verify it by simply using the message we signed, the signature we provide, and so they use Y here, which is our public key. So it is as simple as that, okay? So now let's see how the discrete logarithm actually affects here. The security of this algorithm, digital signature algorithm, relies on 2 different discrete logarithm problems actually. The first one is that the discrete logarithm in ZP star, where the number field sieve algorithm, you can see these papers for more information. So this is an index calculus type algorithm. This algorithm applies to this problem in ZP star, and this algorithm, as I mentioned before, has a sub-exponential running time. But if you want to be precise, the expected running time of the algorithm can be given like this. Okay, here the C is 1.92 and 3. Okay, so it is, as you can see, e to the power this, but due to the numbers here, it is not exponential, but it is sub-exponential. So this is why we are actually choosing our key length here, L, as large, like 3072 bits, okay? This is due to this fact. But there's also another discrete logarithm works here. The second DLP works to the base G in the subgroup of order Q in ZP star. Given P, Q, and G and Y, find X such that Y equals to, Y is congruent to G to the X modulo P. For large P, the best algorithm known for this problem is Pollard's row method, and it takes about this many operations. So, but due to the here, so this is exponential, but this is sub-exponential. This is why we have bit sizes like 3000 and so on. So in the elliptic curve digital signature algorithm, we don't have such a sub-exponential time algorithm. So this is why we can choose bit lengths of 256 bits instead of 3072 bits.